Multivariable calculus. We're on 12.5, day 2. We are asked to find the equation of a plane, and we're given 3 points, A, B, and C. You can see at the top of the screen here I've given a picture, and we'd like to write the equation of this plane. What we saw before, however, in our last lesson is that every plane has a normal vector. And what we're going to do here is first find vectors AB and then AC. That's head to tail. You can see I'm joining them at point A. It's tail to tail, I should say here. Vector AB, it's end minus beginning, so it's ending at B, beginning at A. You can see 2 minus 0 is going to be a 2. 0 minus 0 is a 0. And then 0 minus 1 is just a negative 1. Likewise, if we took a look at vector AC, we'd do end minus beginning. 0 minus 0, we'd get 0. Then we'd go 3 minus 0, that would be a 3. And then 0 minus 1, that would be negative 1. And there you have 2 vectors. What we'd like to do, though, is find a vector that is orthogonal to this plane. And we'd like to find a vector that would make a right angle, not just with vectors AB and AC, but would make a right angle with any point in that plane. And we can do this by finding the cross product. The cross product we already talked about. If we have AB cross AC, a very special multiplication. You could use your calculator to quickly get an answer. For the sake of time, I am not even going to type this into the TI-89. I will just quickly confirm that this is 326. You could also do this by hand. So this is a vector that's going to be, perpendicular, orthogonal to that plane. I'm going to call this point x naught, y naught, z naught. I'm going to call this point A is our initial point. And of course, we could have an arbitrary point. We could have just any old ordered triple on the plane x, y, z, and we could draw a vector here. We could do end minus beginning, x minus x naught, subtract your x components, end minus beginning. Do the same thing with the y components, y minus y naught, and then z minus z naught. This would be just an arbitrary vector going from point A to this point x, comma y, comma z. But what we saw before is that any normal vector, when you have a dot product with an x minus x naught, y minus y naught, z minus z naught, a vector in the plane, because our angle between those two vectors will be a right angle, we know our dot product is 0. So at the end of the day, we know we'd have in here is x minus 0, this is y minus 0, and this is z minus a 1. So we would have 3 times x minus 0 plus 2 times y minus 0 plus 6 times z minus 1. And this for sure is going to be equivalent to the equation of the plane. We could real quickly also distribute here. The reason why I'm doing that is it leads naturally into this next equation that you're going to see in the following example. I think a lot of times we're quite content, correctly so, to say the previous answer that we had is good enough. But if you'd like to distribute, this answer right here would be good. You could even add a constant of this minus 6 to the other side. And that would be the equation of a plane also. They're all equivalent. All right, let's take a look at This next example, we are asked to find where a parametrically defined line right here intersects this plane. And by the way, it's the same plane that we just worked out. So, here is this plane. There's some line that, very well could intersect that. We'd like to find that point of intersection. Tell you what, we could just do a real quick substitution. We can plug this x right in here. That's going to be 3 times 8/3 plus 2t. And then we'll say plus our 2, but instead of having y, we'll write negative 2t. Then we'll have our 6, but instead of having z written out as just z, we'll write it in this form, 1 plus t. And it won't take long for you to see that we could actually solve for t here. When I distribute a 3, I'll have 8 plus 6t. This will become a negative 4t. This will become a 6 plus 6t. And then we can combine our like terms. 6t minus 4t is a 2t. 2t plus 6t is 8t. And then an 8 and a 6, of course, are going to add up to a 14. And we could subtract a 14 and quickly see that we have 8t is equal to negative 8, and see that t would equal negative 1. Now we're asked to find the point of intersection, so what we can do, honestly, is just take this t value and substitute it back in. Well, say this is 8/3 plus 2 times negative 1. Y is going to be negative 2 times our t value of negative 1. Z, we've got 1 plus, well, our t value is negative 1. Well, our z value, I hope you can see, is 0. Our y value is going to be a 2. And 8/3 minus 2, well, that's 8/3 minus 6/3. That's going to be 2/3. So the point of intersection, or x comma y comma z, will be right here. All right, so what we've got coming up right here at the bottom of our page is something that if you were in math team, perhaps you have seen this before. The equation, a formula, I should say, that will allow you to find the distance from a point not on the plane, a point that's elevated perhaps above or below it. And here's a point called P1, and it's depicted by this red dot in our picture. And we've got a plane, ax plus by plus cz plus d equals 0. And, what you're going to see more or less is, we could have this initial point, P naught, is going to be your x naught, y naught, z naught. And if we went ahead and if we just took our P1, which is x1, y1, z1, we could find this vector right here, end minus beginning, head minus tail. So this would be vector B that I've just drawn in there. And of course, every plane is going to have a normal vector. Look, if this is the equation of our plane, I hope it really jumps out at you very quickly that the coefficients of your variables would correspond to a normal vector in component form. So, that vector, of course, is going to be perpendicular to the plane. And right now, we're trying to find the distance. We're trying to find the distance from P1 down here to the very bottom of that normal vector. It's that yellow segment, in other words. Could we find it? Well, I'm not going to go through a rigorous proof of this right now for the sake of time in the video, but it is in our book, and I am going to really stress what is happening, though, and how you could quickly prove it. Here's what's going on. We could slide vector B over here. Remember, a vector can always be slid, same length, just slide it over so that it's tail to tail. And why do I do that? Well, right now, that yellow highlighted distance, I hope you remember, it sure looks like the projection vector's length. The projection vector's length is going to be the dot product. We're projecting it onto vector n. So we could say it's n dot vector b all over the length of vector n. And what is the length of vector n? Well, it's the Pythagorean theorem in 3D, and you could say, well, wow, look at that. That's where this denominator is in this blue formula. You can see that very quickly. Now, as you do your dot product here, that's where you just have to tweak things just a little bit with the equation of this plane and in regard to the x minus x naught, y minus y naught, and so forth. Just a little bit of some work there. But we put absolute value in that numerator because we need distance to be positive. We can talk about the rest of the proof of this formula in class, or you could just read it in the book. But hopefully right now it's very believable to you, and you can look at this and say, certainly I can see where it's coming from. Let's see how we can work this out, though. As I have a plane, 3x plus 2y plus 6z equals 6, you know what? We could, in a heartbeat, just subtract that constant over. You see, you always need to have 0. You always need to have 0 in this formula for the equation of the plane, 0 on that right side. And here is your x1, y1, z1. So you want to find the distance from that point to the plane. And I hope you remember that the distance is going to be ax1 plus by1, so sorry, plus cz1 plus d, all in absolute value. And then down below you'll have a squared plus b squared plus c squared. It's really the length of that normal vector. Well, you know, here we have it. This is your a, b, and c right here. So it's going to be 3 times, we'll plug in your 1 for your x value. 2 times, we'll plug in your 1 for your y value. Your z value is actually a 3. And down below, we'll have the square root of, well, we need our a squared. That's 3 squared plus 2 squared plus 6 squared. Right now, we just have to clean it up. So this is a 3, this is a 2, this is an 18, and this is a minus 6. Well, 3 plus 2 is 5, and 5 plus 18 is 23. 23 minus 6, we're going to get 17. And then down below, this is going to be a 9, a 4, and a 36. Well, I think you can see that 4 and 36 add up to 40, so this is 49. But remember, that's a square root of 49, so that becomes a 7. So it's radical 17 all over a 7. Okay, well, as we press on here, take a look at this next problem. Find the distance between parallel planes. Parallel planes, would look something like this. Tell you what the trick is. Just get a point for your first plane, and then imagine that I erased it. Just look at the point. Right then it becomes a problem like what we had previously. So I'm going to very quickly write 10x plus 2y minus 2z equals 5. But I'm going to let y equals 0 and z equals 0. There is some point on this plane where that's going to happen. And then you'd get 10x is equal to 5. You'd see x would equal 1/2. What are we seeing? It's 1/2, 0, 0. Here's a point. By the way, there are billions of them. There are infinitely many points on a plane.